Hey, we're Group 2 presenting our Strand 7 finite element model of the Jacaranda square walkway structure. Our group consists of myself, Cade Warrington, Monique Finlay, and Zach Wood. So why finite element analysis? Finite element analysis is a method used to solve complex problems that cannot be solved using basic theories. It involves splitting the problem into a finite number of simpler problems that can construct an approximate solution for the more complex problem. When analyzing plane stress problems, Strand 7 will divide the structure into a finite element using nodes and elements. The finite element software will determine the displacement of each node and use these displacement results to compute the stress and strain occurring by assembling each equation into a global problem equation. The more elements in the finite element mesh, the more accurate the approximate solution will be. The linear static structural analysis conducted in this design check assumes that a linear relationship between force and displacement vectors. It should be noted that finite element software does not account for plastic failure in their computations, and so the deflection results may not be realistic. The user needs to be vigilant when analyzing results for this reason, and verifying results produced by Strand 7 is good engineering practice. Our task for this assignment was to develop a replica model of the Jacaranda walkway structure to undertake a design check to ensure it is structurally sound. To determine the structural stability of the model, 5 different load cases were tested, along with 5 more load combinations. These loads consisted of a dead load, live load, wind load, lateral wind load, and temperature differential. Loading cases and combinations used in linear static analysis were developed in accordance to Australian Standards 1170 and reflect the loading conditions the walkway is likely to experience in real life. As part of this detailed structural analysis, a design check for critical structure members has also been conducted in compliance with AS 4100. This will determine if the structure is suitable for continued use. For this project, we assume the following. All joints are completely fixed and have zero movement. There is no friction created between connection plates and bolts. And also, as Sydney has a low probability for earthquake activity, earthquake loading was not considered. And it was assumed that the material for the structural steel components to be grade 350 with a yield stress of 350 megapascals. The steel bracing rods had a yield stress of 250 megapascal. The roof is covered with a protective mesh, and we assume the weight of that would be 20 kilos a meter squared. And now on to Monique to talk about the development of our model.
The team was provided with a set of design plans for the Jacaranda walkway structure. The footing plan, roof steelwork plan, and steelwork elevations plan were consulted extensively to develop an accurate Strand 7 model of the walkway. The plans were imported into AutoCAD where they could be effectively dimensioned with high accuracy for input into Strand 7. The first step implemented to develop the model was to create a nodal map. The more nodes input into Strand 7, the more effective the FEM analysis will be. The plan PDFs were not dimensioned, so the DWG files for the plans were opened in AutoCAD to take accurate measurements. A reference point was selected on the roof steelwork plan where the X, Y, and Z coordinates were set to 0. Measurements were taken from this point to determine all nodal coordinates with a high level of accuracy. The magenta lines drawn onto the roof steelwork DWG showed the X and Y axes, and the white circle the reference point. A similar reference point was used for the footing plan with the same X and Y coordinates of 0. Measurements were taken from this reference point to the columns to find the coordinates for the base of the columns. For the top of the columns, the height of the columns was measured from the elevations plan. To ensure continuity of the column from the base, the gradient of the column was calculated and used to calculate the position of the 3 columns that extend past roof level. These nodal coordinates were entered into Strand 7 to develop a nodal map. The nodes were connected with elements in Strand 7 to create the Y-frame of the structure. Using the provided member schedule in conjunction with plans, materials were assigned to these elements to create an accurate representation of the structure. Further fine-tuning was done in Strand 7 to ensure all rafters and beams were positioned correctly, and fixed restraints were added to the base of the columns. The cafe frame was later added to the walkway structure using the same method to measure node coordinates. The parabola tool in Strand 7 was used to create a parabolic curve with 16 splits between selected coordinate points, producing the circular shape of the cafe roof. The completed design contained 588 nodes and 738 beams. Linear static analysis was performed for each of the load cases developed.
My name's Zach Wood, and I'll be sharing some results of our analysis of the Strand 7 model. After running the analysis of the model, we get a rundown of the maximum displacement magnitudes for the primary load cases. The primary load cases include a self-weight, live and wind load, lateral wind load, and the temperature differential load case. The table gives a rundown of the maximum magnitudes in various planes, with the maximum value occurring under the self-weight load case in the z-plane direction. In this slide, the ultimate limit states are introduced. The ultimate limit states focus on the stresses and failures of members in the structure. The following three load combinations are used to calculate the maximum tensile and compressive stresses on the member. Load combination 1 is conserved with the permanent gravity effect of the structure, with maximum stresses being concentrated in the position of the 250 UB beam. As we can see, the downward force of these forces down here below. Combination 2 is concerned with the dead loads and live loads of the structure, while combination 3 displays the effect of the wind uplift. Similar to load combination 1, the maximum stresses are present in the UB beam for both combinations as well. In the analysis of LC2, the forces produced from the dead and live load combinations are evident in the downward forces along the structure, along this section here. Where in combination 3, the upward action is evident from the wind uplift, if we see the white force lines going upward in a vertical direction. Now we move on to the two serviceability limit states. Serviceability limit states are used to reduce deflections in the model. Analysis of this state is important as they correlate to real-world load and pressures that affect the actual walkway structure. The serviceability state, unlike the ultimate limit state, is not confined by failure stresses and is focused on the deflection of members within the structure. This deflection is shown in millimeters in the two load combination tables as seen below. Combination 4 is concerned with a mixture of loads with the addition of a wind uplift. This combination shows a maximum deflection occurring in the UB beam at a value of 34.6 millimeters. Whereas in combination 5, it's concerned about the self-weight and short-term live loads of the structure, with the maximum deflection also occurring in the UB beam with a similar deflection measurement. Again, from load combination 4, with the presence of a wind uplift force, there is multiple forces occurring in the upward y direction in the structure, as we can see around this section of the model. And then opposingly, through load combination 5, while being concerned with the self-weight and live loads throughout the structure, this displays multiple downward force lines affecting the structure, as we can see throughout here. The verification of the model identifies that there are no abnormalities occurring throughout its analysis. The largest ULS reading occurs at 908 kilonewtons and the maximum deflection is recorded at 34.7 millimeters. The verification of the model is easily interpreted with the aid of animations throughout Strand 7. These animations qualitatively and quantitatively illustrate the model element deflections, allowing for easy analysis. Some problems in the modelling included the incorrect positions of nodes in the model. These nodes were deleted, and through measuring similar positioned elements, an estimate was used to determine the length and position of some of the nodes throughout the model. Another small hiccup occurred when deciding the degree of subdivision used for splitting elements to better display forces affecting the structure. Although the deflections were clear, a higher degree of subdivision could have made it clearer. Ultimately, the model analysis was a success, with results evident well below the ultimate limit states. An acceptable maximum displacement of 34.7 millimeters was also calculated in the structure, while all being in accordance within the various Australian standards that were required. Thanks for listening.